Okay, thank you very much. Okay, I'm going to try to make not an introduction, a derivation, let's say, between quotation marks of ETH. Okay. Please stop me as many times as you want. So when you have a classical model, you're taught Newton's equation, and you quickly learn that the trajectories are extremely nasty in a macroscopic system. And you realize that, except that if you want to land a man in a precise place in the moon, usually you don't want the trajectories. That's not the kind of information it's too complete and useless. And so you move to, or you try to move to other descriptions that are more suitable for a macroscopic system. And in quantum mechanics, you have a similar situation with the matrices of operators, which are full of elements everywhere, 2 to the n by 2 to the n, for example. N is for me always the number of degrees of freedom. And so it's a gigantic mass of numbers. And as you may imagine, they don't contain information that you really want to know, just as trajectories don't. And ETH is a way, it's one way to try to make some meaningful statistics of the elements of matrices, of physical operators in the basis in which a chaotic Hamiltonian is diagonal. Chaotic, I will mean a local Hamiltonian with no particular symmetries. And when it has symmetries, you are within a subspace, so it's under control. So it's not definitely an integrable model. How does this, what becomes of everything that I'm going to say in the case of integrable models is an open subject, and it's quite interesting. And then we can maybe talk a little bit, but I definitely not going to consider integrable systems. Okay, so few preliminaries. So you have a green function. This is an operator. This is a partition function. So this thing, this object here, I will call rho, which is a Gibbs measure. And this thing here is the Heisenberg evolved. Okay. And sometimes I may want to write it like this. Okay, and now, this, of course, you can write, let us assume that T is larger than T prime, okay? So this product is always the sum of the commutator and the anti-commutator. And so if you write this in this way, this is completely content-free. This is nothing what I have done. This thing here is going to be the response function. With the appropriate prefactor. And this here will be the correlation. Just, I would like to say that in general, nobody asks any excuses. I mean, this is extremely easy to derive. You consider the system evolving under a small field up to time t prime, turn it off. This gives you the integrated response. You expand, and this is immediate. The correlation, nobody asks excuses to describing, telling you why this is the correlation. As far as I know, even books don't ask excuses. In the classical case, it's very easy. You start your experiment, you measure the operator at the beginning, you measure it at time t, you record the value, start the experiment again, and so on and so forth. The problem is in quantum mechanics, you're not allowed to measure things at time t prime because you're destroying the system. So nobody, I tell you this because I think it's fun to realize that there are almost, or I haven't seen any justification in elementary books that why is this the correlation? If you want a justification, the only one I know is in the theory of weak measure, where you couple something tiny to your system and then measure the appendage, this ancilla that you are coupling to the system. And from that, you can do two measurements without destroying the system in an appropriate limit, or copies of the system, and then it's okay. You can convince yourself that this is the decent correlation related to that experiment. But what you don't find in books usually, or I have never seen, is this we call it correlation because it corresponds to doing such and such a thing. This is not usually mentioned. You can definitely use this tends to what you want, and this is a Hermitian, which is another thing you want. These two things are true, but relating it clearly to a measurement process, that's what I've never seen. Okay, but all this to tell you that these two, as those who were unlucky to be in my talk the other day, are related via fluctuation dissipation. We are not going to insist too much on that. What I want to do now is do something I did in the day of my other talk. This is, of course, the same as, well, sorry. Here, it's clear that I can put here 0 if I want, because it only depends on time differences. Now I'm going to introduce a quantity that will be useful for us. You see, compared to this one, what I have done is I have chopped into the Gibbs measure, okay? This quantity and its generalizations are going to be very useful for us. But let me first say that I haven't lost anything. First of all, let me say that this one, it's easy to see it is real. And well, yeah. That's more precisely. So why do I say that this gives us everything we want? Because if I now put t going to tau, let's say, plus I beta h bar over 2, the Heisenberg measure here will pick up this beta over 2, which will kill this one, and on this side, it will get together with this one. So by making this translation, I am if you want me to do it slowly, I can. And this gives me it shifts to the right. Notice that this and the exponential in the time will be real, this piece, and we'll get together with this one. Okay, so the point is that if I shift the real axis on the imaginary direction, this function f gives me by analytic continuation this one, and correlations, responses, everything you want. Okay, and this is going to be true for a more general case, which I'm going to say now, just for reference. Let's say proportional because there are H bars, but with two translations, I get either T, the correlation, or the response. When I use, when I use only one variable, it means the time difference. Okay, so from here onwards, I am going to use everything I want to calculate, I will do with F, but bear in mind that I will be able to go back and obtain from it everything just by analytic continuations. More generally, I'm going to define this thing, which again, if I translate this one, I can swallow this rho to the 1/2, take it on this side and translate by different translations in the imaginary direction, which I'm not going to write, but they are, you can derive them. You have to make a little stairs of translations. You can, from this thing, obtain any possibility. You get everything. The beauty of this, apart from all the beauties you will see in a while, is that equilibrium here is based on two properties, and only two. The first is that if I transpose this, what I get is the same thing with the times inverted. So F star, or it just inverts the times. And you can use the cyclic property of the trace. So all of these times are on a circle. Okay? Everything is here. All the possible symmetries. Yes, earlier we were talking with Mukunda about what symmetries you demand on something so that it respects whatever. Well, this is everything. When you have just two, then it's a bit special. When you have these two, they invert. And then, they invert. And then it catches a minus, and then it works. Yeah, because when you conjugate this, you're going to get rho A of A2, rho A of A1, but then it so happens that it's a function of the difference. And so this is going to be the same thing of minus, but because you know it's symmetric, you conclude that F is equal to F star for 2 and only for 2. Yeah, but for 2, it so happens that a cyclic permutation is also swapping the 2, no? So this is why. Okay. And another reason why this object has become, well, the original reason, at least where I got to know it, is that this thing is a celebrate OTOC, and this is the guy that is supposed to go and define a Lyapunov exponent. They decided to define it on the basis of this. Why did they do it that way? I said this on Wednesday. They proved that this guy, regularized in this peculiar way, is the one that has a bound, and not the one, the one without these things. So you're proving something about a Lyapunov exponent on a translated axis. Okay. Okay. Oh, you can play the same games. You can do connected, not connected, and we will do other things at the end. In here, so what they do is they say, okay, it's made of such and such and such a terms, and there is a window, there is a piece that grows exponentially. So they don't. Okay. What will turn out to be the case is that all the calculations we will do are very much simplified by calculating things in terms of this F. If you don't, nothing horrible happens except that you will have hyperbolic sines and cosines proliferating boundlessly. So that's what you want to avoid. I would like to keep, but don't know if I will be able to keep. They can depend on anything, yes. There could be 2 operators and you're playing the same game. The only peculiarity we're doing is chopping the... Okay, how do light cones look in terms of F instead of doing them in terms of the correlation? That's interesting. They smooth out, but you get basically the same structure. And I wonder if nobody has done it a lot, but it would be interesting to see it in terms of F, because F is a nicer function. Correlation and response are valid on a strip, and where you look at them is at the boundary of the strip. So they are just about to be non-analytic. And instead, this function F is straight in the middle of the strip of validity. So this is why it has nicer properties. But okay, but it's just a reshuffling of the variables. Okay. Now, this is the heart of what I'm going to tell you is the following concept. So imagine you have a system of spins with energy between 0 or between something and something. So it will have, in terms of energy, many levels. And you know and you expect that the distance between them is going to be something like 2 to the minus n, distance in energy. Okay? We are accustomed to this this is what happens. The level spacing is exponentially small in the size of the system. So sometimes we will, often, we will do the following. The change in the number of levels of, let's say, E, we're going to write it as a continuous thing. So this is simply when we have sums over the E's of something, we will approximate it by integrals of that something, and the weight is how many of these levels you have per unit delta E, and this number is the entropy of the problem. Okay, so remember, and this is going to be very important for everything, when I go from sums to integrals, I pick up a factor entropy. Okay? Okay, now another thing. Imagine that I have a Hamiltonian and I decide to perturb it with something like, for example, the size to some power times a perturbation. This would be, I have my solid state system and I bring an electron and put it a meter from my sample. This is a perturbation of order 1 over n. Of course, you don't expect the physics to change very much, unless the system is integrable, in which case, yes, you would expect it to change. But if the system is not, you wouldn't expect it to change very much. So the perturbation, this perturbation is negligible. But it is negligible with respect to the physical properties, macroscopic properties of the system, correlation, responses, many point correlations, etc., energies, expectation values of physical operators, etc. On the other hand, if I have to compare this scale of energy with e to the minus n, the level spacing, this perturbation is enormous because n is large. So this is what I mean by small but big. And the whole topic, the whole lecture is based on this, that you have perturbations that do nothing to your physics, and yet they are gigantic perturbations from the point of view of perturbation theory. Just so that to convince yourselves, you take a 2 by 2 matrix and as you know, in a scale of order delta E, the eigenvalues go like this, and in a scale of delta E also, the wave function, which in this value is psi1, becomes psi1 here, and if it's psi2 here, it becomes psi2 here, so that, for example, an expectation, this one I'm going to call 1, and this one I'm going to call 2. An expectation goes from being psi1 to being psi2 in this very small interval. And the same is true of a matrix element, which goes from being psi1 to being its conjugate. Or something, I don't know. But not necessarily. Okay, yes, it's conjugate. So this is a first indication that the scale at which things get horrible between levels is when you perturb of the order of the level spacing. But this perturbation is perturbing way above the order of the level spacing. Another way to convince you is that formulas you learned when you were small, or even worse, this one would be, if you want, the W that I introduced before. So you see, wave functions are extremely sensitive to this thing, which is your interaction divided by the energy difference. So that's the scale that counts. So it's obvious that this perturbation theory will blow up and become meaningless, but also the perturbation itself is going to become really large as soon as my perturbation becomes comparable to the level spacing. But this perturbation, which is physically entirely meaningless, irrelevant, is gigantic with respect to perturbation. It's exponentially larger. So this would be, I think, the analog of, in a chaotic system, a tiny perturbation will make the trajectories do whatever. So now we have to try to make, so because the matrix elements, for example, of an operator are complex numbers and they are being perturbed madly by an unphysical perturbation, this is what I would call the roulette phenomenon. Roulette works on the basis of taking numbers modulo 2 pi. You make them turn fast, and automatically this is an analog computer that makes it order 2 pi plus the randomness of the ball, and this is the way we generate random numbers. This is doing precisely that, okay? So just to be more sharp on this, when I do this perturbation, I have an operator A, which I am writing the operator, I will say it's phi. Yes, we are assuming throughout, and I will progressively say this. For H, we already assumed it, that it is chaotic, but we also assumed that it is a local, decent, more or less reasonable thing. And of course, if you do whatever, clearly, if you could engineer the things in order to get what you want. But yes, you're assuming that it has no particular structure. All these things, if you ask me to become rigorous, I will change subject, because these are things that are extremely intuitive, but it's not likely that any of this will be proven really. So I write A in the basis of H, 0, and I write A in the basis of H, which is a small but big perturbations. And of course, this is some transformation, which is the transformation from the diagonal basis of this to the diagonal basis of that. And what does it look like? Well, what we expect is this perturbation, this is the scale of total energy. In these terms, the perturbation is tiny. The scale of level spacing, on the contrary, is very, very small. So we have these three scales: the energies we're interested in, the level spacing, and the size of the perturbation. So by all these arguments, and this again is quite heuristic, but you can try it in every model you want and you're going to get the same thing. This matrix looks more or less like this. This is the unitary matrix U. Okay, so by the way, these ideas, although perhaps not expressed, but clearly there, but not expressed quite in this way, date back to Deutsch, probably Berry to Deutsch, and Srednicki in the 90s or even a bit before. Okay, so that this is from the lowest to the highest energy, I have a difference of order n times 3 or 4 or 2, okay? While these guys have a separation of 2 to the minus n, and my perturbation has a strength 1 over n to some power of this. So so it doesn't couple far away energies. Look at these formulas. But it does couple nearby, only that nearby I have a lot. And yeah. We will do all that. No, it depends on the system. It happens to be exponentially, and I will tell you where to look for that. It's a review that Marcos Rigol, who's not there anymore, did with Luca D'Alessio, Anatoly Polkovnikov, and Yarif Kafri, and I recommend for the first part of my talk, this is a very good review. Okay, so what is our task now? Our task is to be able to say things modulo an ensemble not very well defined of transformations of this kind that are small but big. And we will try to guess what survives of a matrix when we do something like this. And knowing that all these matrices where we bother them we perturb them this way are going to have the same physical properties. So we might just as well consider that that term is there, okay? And what is this operator doing? Basically, it's getting the levels that are more or less near but far in the sense that they are differences in energies that are small with respect to the interesting energies, but enormous with respect to the levels placing, and it's twirling it locally. This local twirling that done by this is our ensemble. It's not a group, so I cannot even define it as an ensemble, but it gives you an idea, okay? So our ideal would be, if we could do it, to define really an ensemble with a lot of operators, and then do averages over perturbing over those, but nobody has done that, and maybe it's too much. Anything you like, but generic. Generic in the sense short range. Of course, you could in W put an operator that has 0 everywhere and 10 to the 24 in the position 8, 4, no? But that's not, you're perturbing with another physical operator. So both H and W doesn't need itself to be non-integrable, but H, we will need it to be integrable. And then it will turn out that, well, nobody really knows, but yeah. Okay, so the question will be, what happens when I transform things like this? So I will first take you through these things, talking, and then we will try to, we will need to learn how to do it a bit more seriously. So, so imagine that, let us look at the diagonal part of my operator A. Imagine that the matrix were purely diagonal, it would be left invariant by this transformation. If it's locally invariant, I'm talking only of the diagonal. I have cut the rest and put it to 0. If I have something that essentially is the identity over a set of levels, you see, you are working with something that is essentially a unitary that mixes things. And we will do this mathematically, but I would like to give you the feeling that the AII and the AII transformed with you are going to be very similar. If this doesn't convince you, we will do it a bit better in a second. To show you a completely different example, consider an element here, and I am transforming with this law. This element is going to be hit by this matrix in different places on the left and on the right, and it's an enormous perturbation of the levels, and so this element, we expect it to change sign a lot of times. So the idea is that this element is going to randomize. We will do this in concretely. And so we should expect its phase to be basically random. And as we shall see, its amplitude, no, we will expect it to be self-averaging with respect to these transformations. So what I am doing is I am taking a typical operator A, I am applying these things to them, and I'm looking at how things change. And what I notice is that along the diagonal, if things depend smoothly on the diagonal, then they stay invariant, basically invariant, and things that are off diagonal, as we will see, retain their amplitude, but their sign changes like mad. So we will have to make an ansatz for this situation and try to justify. Srednicki guessed it, and he did it in the 90s for the two-point function. What will happen to us is that we will realize that his ansatz needs to be completed, and when you try to complete it, you need to be a bit more precise what you mean, because otherwise you don't know how to continue. Okay, so the ansatz, the first ansatz of Eigenstate thermalization hypothesis is to say something about what happens in the diagonal, and what we say so what do we mean by this? We mean that we are taking the diagonal elements, and we are saying that along an energy difference, again, that is small but big, it varies smoothly with the energy density. So it's across many levels. For any observable, this thing on the diagonal varies smoothly. It does vary, but for that, you need a real energy difference. Here, we are going in a small but big distance. Okay, and this gave the name to the ansatz because it's called Eigenstate thermalization, because it meant, I think, that A is like spread on something that you want to think of it as a shell. It's in phase space, so you would need coherent states or something like that, of Wigner functions to see it. But it says that essentially this is a very smooth function. Okay, this is the first part of the ansatz. Very well. The second part of the ansatz concerns outside the diagonal. So we had the diagonal, which we did already. This is the matrix A. And now we look at what happens with A, and what happens, what we will try to convince ourselves is that the matrix elements of such a matrix are decreasing in modulus outside the diagonal, each one is extremely tiny. You will understand why, and we will check that it is so. The way in which it decreases, it's along differences in energy of order 1, energy, total energy. Along the diagonal, as I say, things vary with the energy density. So this is much narrower than this. And the individual elements are tiny and random. So what Srednicki wrote is the following thing. The diagonal term, in terms of the energy density, plus the going down slowly, it's done by a function f, which is a function of, let's say, the average energy, which doesn't change much, but it depends slowly on the average energy. So it depends along this direction, very slowly on the energy density only. And then it depends on the energy itself. This is this direction in which it falls. You asked me, I think, if this falls exponentially. In practice, it does. But it could. I can cook up a model that doesn't, but in many models it does. So it has this. Then I told you it was random. So these numbers are going to be order 1. And then it has, oops. You think that this will not? Okay, so let's go through the terms. This is what Srednicki wrote in the 90s. So this we already discussed. This is the envelope that goes down smoothly, depends on the operator A and on the Hamiltonian. The only thing you're assuming is that there is some envelope of this form. And this is...
there's a half in the exponent, isn't it? E to the power minus half, or not?
Here, yes, there is a half. This is an exponential term, and this is a random number of order 1. Before you ask me, this I can put whatever I like, because otherwise I can put the rest in here. So I'm putting this one because it will make F easier. I'm putting this one of variance 1 because it will make this one easier. And now my claim is that this one is order 1, nice, and everything, okay? That's the part that matters. And this depends on the operator and on E.
So there are two ways to, there are two classes of diagonal elements that you might consider, right? So you can, for instance, choose Mn in such a way that the corresponding eigenstates, they essentially correspond to the same thermal state. Or if you want, they are
relatively near.
Relatively near. In that case, I mean, actually the scaling with the e to the minus s holds also for integrable systems. But you could, in a different way, decide to choose M and N from, let's say, two thermal ensemble with two different temperatures. Would that remain valid, or because in integrable systems, if you do the numerics, you see that they decay much faster than, I mean, they decay.
Two different ensembles, you mean from two places in the energy that are very far away?
More precisely, you could fix the energy density, and then you can sample around the two different energy densities, and you consider the corresponding matrix element.
So what ETH says here is simply the prolongation of the formula we will find for F. There is, as far as I can see, no particular structure. I think that it could be the case, but it also tells you that they're going to be super tiny. But in any case, they are so tiny that it will be a large deviation, for sure. Now, nobody, as far as I know, has done large deviations. You're talking of things that are exponentially small. Will this need to be refined to get exponentially small elements? Perhaps. Nobody has done it as far as I know. You expect, obviously, less structure than in an integrable model, but what exactly happens, I don't think anybody has.
It was not clear to me whether this less structure would enhance the off-diagonal or would furtherly suppress.
Neither. No, I don't know either. But it's a nice question. Nobody has repeated the arguments I'm going to make here for that. So,
for integrable systems, numerics suggest that they decay as e to the minus L square rather than e to the minus L, which is
that's
entropy.
interesting to see whether this kind of progression. You will see now, and we can see it together, if the arguments I make, to what extent they are valid to that.
Thanks.
Okay, so this is what Srednicki did. And now we have to decide what F is. Okay, so now what we're going to do is very easy. We are going to take this form of Srednicki, calculate a two-point correlation function, the one I introduced at the beginning, and we will get that it's going to be simply related to what Srednicki put here, but the only thing we have is this and this in reality. Okay, so we will do that, and then we will get how this and this are written in terms of the actual correlation functions, and we are done with justifying Srednicki, okay? But as I told you, we will not use correlation functions, we will use that F function, because otherwise your life is marred by a profusion of hyperbolic functions. So we will do it with the F.
Jorge, one question. So when you say this diagonal part is smooth, like how smooth what do you mean?
I mean that to the leading order, it's really a smooth function of the density of energy density. And it has tiny fluctuations which go beyond the theory that we will do today and have much less been discussed. Exponentially small. Yeah, very tiny. They are of roughly the same order as the off-diagonal elements, so they scale more or less like the off-diagonal. But that's very small. Actually, no. Actually, all physical operators are like this.
Even local operators are like that, you're saying?
Precisely, local operators are like that. Roughly anything decent, because an operator that to you seems local because it's one spin in one place, in the basis of eigenstates, it's terrible. Now you could tell me, but if I have many body localization, that is not true. Precisely. Many body localization is defined as a system where ETH doesn't hold.
Yeah.
Okay, to be clear.
What do you know about this RMN and these random variables RMN? I mean, are they correlated or independent?
That's the second part of the lecture. For the moment, we will not need the correlations. People were rather quiet about it because when you calculate two-point correlation functions, you don't need the correlation between them. But then you realize that it is meaningless to say that they are uncorrelated. Okay, so just to give you an example, just to get a bit the techniques, where is it? Okay, what we will do all the time, let me do one calculation, for example. I have Z, which is so as I mentioned before, this we will convert it into an integral. I suppose that obviously this is something you know. This I have made the sum continuous, and this I can evaluate by saddle point, and the saddle point is, which is the definition of temperature and canonical, microcanonical, etc. So you evaluate there, and that's what that gives you your free energy. So let us do what we wanted, and using this kind of trick, calculate f of t. So this is and I am going to normalize it. Sorry, normalized. No, divided by Z. Have a look at it. What I have done, maybe here I skipped, this is the trace of e to the minus I over h t h a e to the plus e over h bar th rho to the 1/2 a rho to the 1/2. Now, and divided by the normalization. Look at this, look at that, you will see the same terms. This one gives you this difference. These two on both sides give you this difference, and A and M appears twice, okay? Convince yourselves that this is true. Now, what we have to do is to use Zrednicki's ansatz, but before this, let me write it in a more convenient way for us. This same thing we can write like this. With this thing being the modulus squared of this thing. I just took the modulus of the formula above, okay? This is more convenient for us. Okay, so this big F is just the square of little f, and we still need to decide what big F is. And the random factors disappeared because I assumed that their average is 1, their variance is 1. I assumed, and it's not a big assumption, up to a certain point. It's not a big assumption because I'm throwing things, but remember we are assuming smoothness in things. So we are assuming that these guys, their amplitudes are not very wildly oscillating. So, I have, in a way, taken the expectation value of Rmn squared. This is the first step of justification. This is what you got, you will find in the review of our friends and what Cerny did. I am going to, but there is the assumption that things have been twirled so much that locally they are smooth, and this I will try to give you a better justification of. Okay, so here we will separate two parts. First of all, the diagonal. This sum we will split into diagonal plus off diagonal. By the way, I should have been more clear. The diagonal, apart from being smooth, is enormous compared to the off diagonal. So there's good reason to separate it. And okay, the diagonal is easy because now n is equal to m, and we apply our formula, and this disappears. And so the diagonal is equal to and now I'm going to really be serious about the normalization. And here I just put E of E over N, the function I squared. And remember that when I go to integral, I have to add an entropy because that's the level spacing. And now here I'm dividing by and this is, you see, this is a function that has a saddle point. This has a function that has the same saddle point. The only thing these two guys are doing together, they are so peaked that they are evaluating this in the saddle point, and we simply find in the saddle point. So now we know what to put in the diagonal. It's the expectation value, the diagonal expectation value of the operator we are doing in the basis we're doing, okay? So we discovered what this has to be. Is it okay? The argument of saddle point is that this is a saddle point function, this one too, and this is only a prefactor. And you know that when something is saddle point and normalized, it just evaluates a prefactor in the saddle point value. Okay, and now the off diagonal, they are. No, we're in the diagonal for the moment. Now in the off diagonal, as you say, there are going to be two integrals. Okay, in the off diagonal, so we're going to have and now, well, the numerator is the same. And now I need to put the off diagonal part, which is R has gone away, e to the minus s of e, en plus em divided by 2. I'm just copying the formula at the other end of the board. And here, the famous F2, which is a smooth function of the en plus em over 2, and is a function of omega, defined to be en minus en. Okay? Good. And as you say, I am going to convert this into an integral. And the integral, this one comes from ETH. All this is ETH, okay? So this is going to be d prime e to the minus s of em plus en over 2 plus s of en plus s of em. This comes, sorry, e plus e prime, yes, sorry. This comes from the measure. Then we have minus s of omega, I'm calling directly the sum omega, and plus, no, what am I saying? S of, these are okay. Now I have f of e minus e prime, which is omega, and that's it. And now e to the minus I t over h bar em, well, omega, but en minus en. And this I have to normalize by the integral, okay? E minus e prime, thank you. Okay, I just plugged everything in. And now you understand why Srednicki put this tiny factor in the matrix elements, because you catch twice the level spacing, and this has to scale this way so that the total thing has an entropy only once. And the lovely thing of this is that to first order, and you only need first order, this is simply S of E plus E prime over 2 once. You are assuming that E is close to E prime, and here I think, Vincenzo, we are entering your territory, which we are quickly moving away from, because we are saying that the energies we are considering are not gigantically different. And now it's very easy. You change variables E minus E prime into E minus E prime over 2, E plus E prime over 2. This integral, so this you change into dE plus, let's call it, and d omega, difference and sum. And you see, this part is only going to give you the saddle point you have below when you integrate, because this gives you only one S. And this will assure that the normalization works properly and can be evaluated. And the beauty is that when you integrate d omega, what you find is remarkable is that, sorry, this is the F2 from ETH. You find that F2 from ETH of omega equals E minus E prime is exactly equal to the Fourier transform of f of t, the one I introduced before. So this, you see, because this normalizes with this one, and this one, you change variable sum and difference, and this is nothing but the Fourier transform of F2. And so what you discover is that when you write a matrix, the way it goes down is an F2 in modulus, which happens to be f of t, the correlation, the one that I defined, Fourier transform. We, a posteriori, have shown that the idea of plugging out, of taking out this factor, that's the idea of Srednicki, was the good one so that we get the right scaling. If we had chosen otherwise, it wouldn't have been bad, but this relation would have been more complicated, no? But this is the only truth of life. So now we know everything. Okay? By the way, another thing about thermalization, of course, you surely have heard of this. If you are calculating psi, if you're calculating correlations in terms of time, this gives you this, and the usual argument is that off-diagonal terms oscillate, and hence oscillations die. Of course, this is a cheat because nobody is waiting for Heisenberg times to see a correlation decay to zero or to its final value. It's a mathematician's argument, but we are expecting that things fall to zero way before the, this kind of argument doesn't say much. But this explains why some people say that eigenstate thermalization hypothesis talks about thermalization in the usual sense. But I don't know. Okay.
So how time enters the game? Because if I imagine always of taking a long time limit,
Yes.
is it safe? I mean, could it spoil or if you want, the question is what you wrote valid at any time or only in the or you are assuming some long time limit?
No, I am not assuming things about time except if I began to scale times in a dramatically different way. So I am a bit afraid that the question you're asking, perhaps the subtle points I do because I balance things. But as usual, when you're doing a large deviation, you have to be careful. So if you are going, you see, I used that energy differences were small to make Taylor to second order, and the second order drops off, and this is why I said that all this is S. But if I don't do that, then no, then this is this. And then you have to make this integral. You still can change variables to the sum and the difference, but it's not as neat. You get an extra term. So I think that you get an extra omega dependence that is not in ETH normal if you're going very far. So this is one of the things that we have to treat it with care. What we learn is that then short times are very off-diagonal elements. Long times get more and more close to the diagonal, as you would expect from the usual argument. Yes?
So just a bit confused about the notation maybe. So it's F2 omega is equal to F hat of T. So where did the T go?
Where are we?
So in the
difference here, yes.
yeah, but no, this equation that you have.
Yes, F2 of omega is the Fourier transform. So it's
okay.
Okay.
Okay, thanks.
A rho half, right? So instead of if you did this for the regular correlator, I mean,
you would have a problem here that this expansion, instead of being symmetric, you will need to, you're expanding in small energy differences. So you would need, the first order wouldn't cancel, and this comes down as a derivative, which is an energy, and then it gives you a hyperbolic cosine or a sine, which you will get with this approach also, but you first do it with F and then you do the analytic continuation and you will get it. But this is why the symmetry of this thing that comes from the fact of taking the rho to the 1/2, rho to the 1/2, automatically kills all the sines and the cosines. That's the only thing. So if you go to the review of Marcos and Anatoly and company, you will find it done with a usual correlation. And the only thing is that you have to drag with you these factors that come from this expansion.
You can still do it, but this is simple.
Sure, sure, you can do it. But when we go to the many-point correlation functions, it becomes an absolute nightmare. Because then these differences, if you cannot neglect them, it proliferates. Yes?
See this from the Fourier transform.
No, there is a part which is a definition, no, which comes from ETH. But these guys come from, no, the S is no, but sorry, this factor here, this one. No, where are we? This one. This one came from putting 2 rho to the 1/2.
Yes.
If not, you would have beta En. And so this would not, sorry, I'm correcting what I said to you. This one would not depend only on the sum. It would be En without the Em. And so it would become an omega because you want to write it in terms of sum and diff. That omega that you pick up here is conspiring here to give you a hyperbolic cosine. So if you didn't do it that way and you did only 1 rho, you would have beta En and nothing else, which you would be forced to write now when you change variables, divided by 2, and this one will be what we have now, but this one is an omega. This extra omega, beta omega, plays a role in all these things and translates this difference, and this is what makes your life miserable. Well, miserable. It's only a hyperbolic cosine, no, but.
Your comments on thermalization. So, normally I would expect that in a non-integrable system, this level spacing would go as e to the power minus n. So that was your comment, that one would expect thermalization to happen at the Poincare recurrence times at e to the power n.
Mm.
And of course, thermalization happens at a much shorter scale. So how do you understand that? I mean,
You don't. You don't. You just say f of t is my favorite f of t of a model I like. I can, people say, this is the Fowler scale. Well, no, it's, if I have a glass, it's not the Fowler scale. It's the glass scale, which is gigantic, enormous, the age of the universe, more or less. So it's just your physics. And the physics, I'm not assuming it here. It's what f wants to be. And so I have no argument. What I claim is that this is not an argument for thermalization. Your argument for thermalization comes from saying what your F wants to be. Okay, up to now, what I assumed here, we have now bits and pieces. We now have what this has to be equal to and what this or that has to be equal to. We don't know anything about the correlations, but what is left that we should prove, or at least convince ourselves, is that this function is a smooth function of the energy density, and that this function is a smooth function in the direction of the energy density, and it's a function of the energy difference alone, and it doesn't jump madly, it's a smooth function. So the fact that f is a smooth thing, which depends slowly in that direction and rather faster in this one, but smoothly. The smooth part is that what I said about twirling locally with a unitary operator, but I didn't give you anything convincing. So let me tell you why we wanted to convince ourselves a bit more. The story of this is that, as far as I know, Cerny was teaching and wanted to do something like that, and he did it, basically, and then he took for granted that this had to be known. He's a field theorist, not a man of... And so but he couldn't find somebody who really had done it all. So, well, and then nothing much happened until Marcos and Anatoly, etc., wanted to write a review on this. And basically they discovered Strelnicki's work and made it known to the world and added a lot of things. And then, okay, this became super popular. And then there are millions and tons and trillions of verifications that this works. So nobody doubts that this works in systems. The only thing that is not really tautological in what I did is the assumption of smoothness of FNA. That's really the only true thing that is you have to convince yourself. How will we convince ourselves? I will tell you in a second, but now let me tell you why we got interested, because this will convince you that this doesn't work completely. As I said, and I wrote somewhere, you need a 4-point thing, f of t, 0, t0. So it's like our favorite function with rows, but with 4 of those to calculate the Lyapunov exponent, okay? You read it in the papers of the relevant people. And so we said, great, so we have that formula. We take it, we plug it into the formula with the 4 things, and we calculate the OTOC with ETH, and so we will have an ETH theory of the Lyapunov exponent. And then you think a little bit, and you realize that this is nonsense, because you now know that the only thing that you have in your ETH usual is the 2-point correlation function, a 2-point correlation. And how am I going to get a 4-point correlation function for free, generically, model independent from a 2-point correlation function? Life cannot be so good. If the people who did the Lyapunov thing did it with 4-point correlation, it's not because they are stupid, they did it because that's the quantity you have to look. So it is clear that 2-point correlation functions cannot give you 4 correlation. Does that convince everybody? So 2 minutes thought said, this cannot be contained in there. So something must be there in the 4-point correlation function that is not there. So with this argument, I think anybody can be convinced that ETH was incomplete the way it was. Is it okay? Okay, so how do you do progress on this? So our aim now is going to be able to reproduce things like the ones I did at the beginning.
The thermalization is concerned, I mean, this is enough, right? I mean, so if you, for the 4-point, it doesn't tell us anything more about thermalization, is that correct? And because all physical quantities are...
Yes and no, because when you have 4 times, you can keep, okay, the first and the last far away from one another, but then the second one can be somewhere in the middle, where in the middle. So, I mean, you have many possibilities, no? You can send to infinity different things.
Things like physical observables are like, if I'm measuring anything.
You mean 1-point functions? Definitely nothing new.
But even 2-point like correlation functions, dynamicals or whatever.
We are not going to modify at all that. We are going to complete it only. This does not get modified.
But are there any extra observables that I can learn from the Lyapunovs?
Well, the Lyapunovs are super interesting in themselves. Not the Lyapunov, the OTOC, which doesn't have a Lyapunov growth. As you know, the butterfly and all that is very, very interesting. Now, are there other animals, for example, 6-point things, OT, 0T, 0T, 0T? Do we learn something from that? I think it's largely open, this thing. this has, I don't think, been so much explored. I think that what is interesting, all these things are interesting. Lyapunov in itself, not so much, because of the reason that, you know, physical systems don't have a Lyapunov, a quantum, you know, chains and things like that. So, okay. So now our aim is to, we would like to be able to do let's say proportional, and it will be normalized, rho to the 1 over q, T1, sorry, A of T1, rho 1 over q, A of T2. We would want to calculate things like this. I remind you that the one that works for the auto is T0, T0, and Q is 4. This is the one that was considered by the people who proved the bound. And this is the one that is where you, if you put this inside there, you get nonsense. Okay, so we wanted to say, okay, where does all this, where can it fail? And the conclusion, which of course all of you, or many of you asked already, is here, no? I cannot, the only place where really this can fail is to say that the R's, the random numbers, are correlated, and it's not true that they are uncorrelated. That doesn't make this worse for two-point functions. It didn't enter at all, the correlation. So it doesn't change anything that our friends wrote in the review. But it will be important if I want to calculate a four-point function. Okay? So this is the part that doesn't go. And now we will have to try to make an answer. How do we make an answer that is general? So let me try to say how you how do you get convinced of ETH a bit better? This is very, very far from a proof. So, okay, so we would like to see how things evolve when I change basis this way. Remember what was the argument? These unitaries are changes of basis that operate on observables when you get an electron and approach it to your sample. This is a perturbation that is order 1 compared to our system, which is order n. And we don't expect anything to change, but this is a big thing for the elements. So this is the kind of thing we want. Now, what we did with Laura Foini is that we said, okay, no hope whatsoever of knowing what to do here. So let us do something cheap. Let us imagine that U, metaphorically, is not of that form, but is made of little blocks. All of them are unitaries, different unitaries. Then, if necessary, we will add other blocks that will mix that, because if not, these will not mix in themselves. But with these blocks, we will be more or less done. So this is just heuristics. Really, nobody knows how to do better. We will try to see what happens when I average over such things and guess that those things do more or less the same. Of course, I will have to be careful where in the blocks I put things, but the blocks are small but big. Again, they contain many elements, but they are tiny respect to total energies. Okay, let me say that I found out later by Masahito Ueda that such a unitary matrix cannot come from a local Hamiltonian. So take it as purely metaphorical, but it's nice because it shows you the way. So now, what you do is the following.
Yeah, hi. So the second moment of RMN entered the conventional ETH, right, for the 2-point thing. Here, it's evident that the 4-point will occur. Can we not just put some assumption on that directly?
It's true what you're saying, but we will not use RMNs anymore. What we will do is simply say things about correlations of matrix elements, which amounts to the same. So we will discuss what is AMN modulo squared, what is on average over those matrices, or AMN itself on average over who, on average over those matrices, and so on, and 3-point objects. And our task is to consider every possible combination of M. Now we are not calling them Gaussian, so this you can get from the R's, but it's more complicated. So the only thing you have to say now is who are the guys that can survive this? Okay, so let me give you an example that I think will convince you. Let me say that I want to find on average what does Aij for I different from J. What does it look like? So I'm going to average, I would like to average over these things, because I would like to say, this is what really happens when I bring an electron from the end of the room. But I don't know how to do that. So I'm going to average over these guys. These guys are made of matrices. Let's say that the element I happens to be with the matrix U1, and the matrix and the element J there happens to be with the element U2. And now I'm going to rotate this and see what happens to that matrix element Aij. So I have invented a fake ensemble and hope for the best that this tells me things about how this other more plausible thing should look like, okay? This is the best we have. I mean, it's not 100% satisfactory, but that's what, yeah. These are, the blocks are, first of all, big but small in the way, are independent. So now we are back home. So just to say, when I rotate this, you see I am doing, I am rotating my matrix A by this thing that had a little block in where I lives and had another little block where J lives, R, big, etc. They are near because these blocks are small but big. So they contain many levels, always the same story. And then here I have J. Okay? So Aij, if I do this, is transformed. You see this had a U1, this had a U2. This is going to be transformed like U1 IL, U2 MJ. You see it from here, and here A M L M. Okay? And now I want to say, morally, I would like to average over these, which is a proxy for averaging over this, which is an argument of typicality. There is an enormous literature on typicality. Typicality means that your operators, when you average over a certain set, they are typical members of that set, and then you have to decide which set. There's a, I think the thing goes back to von Neumann, and via people like Joel Leibovitz and others, the Shelley Goldstein and lots of people have worked on this. Here is one more argument on typicality. No? It's the typicality of moving around an electron around the room and seeing how your elements change and assuming that there may be an electron and things are stochastic with respect to where I put the electron. And because not even I can do that, we average over that proxy, which more or less we hope will do the job. But now it's quite easy because this we know how to do. The matrices are hard, independent, etc. Yeah.
I think of these blocks that you wrote there as containing eigenstates that correspond to the same temperature or energy density macroscopic.
Even smaller than that, even less, even more sharp than that. Not even square root of n. I can make them 1 over n to the 4th in size, okay, which is still enormous because it's exponential. So okay, I can make it even within the Gibbs bell, let's say.
So then it's the other way around, that I can think of the entire matrix as representing a fixed energy density. I mean, because...
You could if you want.
Yeah,
you could if you want. Yes, you could if you want. So now you're averaging, but now this one is independent from this one if they are in places that are different. And when you average, these averages exists. This is the Weingarten whatever, but doesn't require so much. When you average over unitaries, sorry, over the Haar measure, the measure of all unitaries. So you turn this one around like mad, the average of this is 0, and the average of this is 0. So you conclude that if I move the electron at the end of the room from one end to the other of the room so that the interaction changes a little bit, this thing will vary wildly in such a way that its average is going to be 0. Okay? This is as best as we can do, the best we can do, more or less. On the contrary, if I do AII, now the two have to be in the little same block, and now I get U1 IL, U1 again, MI, probably not, and A, LM, no, L. Here it is, and here A, LM. IL. Probably. And now I average this thing. And now this gives me delta IM. This is known. This is a matrix times its transpose, so it's the same matrix, so it's the identity. So now these little blocks, it's the same block now, give me this average is no longer 0. And this gives AII, and we are happy. So what this means is that, again, if I look at a diagonal element and I move it around the room, my electron, the diagonal element doesn't change. It changes a little bit, but on average, it doesn't change. So what do we learn? We learn that for AII, we need to assume that it's not 0. Then we will have to discuss what it is. Okay? And sorry, I think did I do it right? This one gives you delta ML when you average it. This is the same average, and yes, you get that. Okay? So this is plausible, and now let us consider another one. We want to know something off diagonal, so let's do this. Same thing. I consider that this one, this one, this one, and this one live in different blocks. This one will be turned, so we will have the block M contains a U1, the block M is here, N is in a block U2, and I is in a block U3. I rotate this one with these two, because these two, I'm doing exactly the same calculation with a block matrix. I rotate with this one, I rotate with this one, and I average over these. And then what you quickly realize is that the kind of average that appears here is going to give you 0, because there is this unmatched U3. So this one will be U1 something, U1 dagger, U2 something, U3 or something like that. And you realize that an average alone over U3 will give you 0. So the rule of the game is to do these rotations with a little matrices. Go to your favorite review article on this. Binacker has a very nice appendix on this that is unpretentious and easy to read on averages of unitaries. And you realize that this is going to, on average, over this ensemble, the one there, it give you 0. On the contrary, and this one I will do it, I think, in better detail. Let me try this one. Okay, this one is a candidate to being non-zero. We have been using it all along. So this thing, we hope it resists this twirling. Okay, so now I'm going to do it properly. This is U1 I, so U1 I K. And now I have to average this one, which is a 1, with this one, which is a 1, and this one with this one, which are 2s. They are separate variables. And now this one, when I average, I go to my favorite book, and this is delta of LM, average over all the unitaries, and this one is delta Kn. And you conclude that this is invariant. You put all the deltas and you see that morals of this is this quantity will not have an average different from 0, but this one has a right to have 1 because this twirling doesn't destroy it. Is the logic clear? So in this way, so this creates a justification of why Srednicki chose those numbers. How much time do I have left? 20? Okay, so it's going to be short, but you will get the idea anyway. So is this clear? Because I'm going to just go on now. Now, the only thing we have to do is we want to generalize this. And I'm not going to introduce R's, but I'm going to try to find out what the average is under such a process, which tries to mimic such a process. What are the average of objects like We did it already. We did it already. But now we will want to do more complicated things. Now and onwards, when indices look different, they are different. Okay, they cannot be equal. We separate the, so I1 is different from I2, I is different from J, and so on. Okay, and this kind of thing. So how are we going to proceed? We are going to do these things, plug them into the matrix of little blocks, and see if by the twirling operation with the unitaries, they have averages that are 0 or averages that are not. This thing I can do like this. I can write an I, and I can do it like this, an I and a J, and do it like this. This one, an I, a J, and coming back. And this one, a circle. You see how it goes. And I could even do do you agree? So rule number 1, and how do I do these things? Typicality. I rotate with my favorite matrix, rotate, 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 and see whether the average is dying out because of the unitary thing. First rule we learn, we've already seen it, is that when there are things like this that are dangling, this gives you 0. So the circuits must be closed, because otherwise you can go to the Weingarten calculus, but it's easy to convince yourself that otherwise there's an angle that is always left and kills all the averages. So this one is okay. This one we've just done. This one we will find it's okay. And this one we will find that it is, it's definitely non-zero, but we will see that it will be subdominant, but it is definitely non-zero. So now we immediately throw all averages of element. This is not summed. This is just an average with those indices, and where indices look different is because they are different. Okay, so we have these terms, and now we have to plug all the A's in our original formula and see what happens. And we will get lots of terms with many matrices, and we will have to decide which averages. This one and this one are in ETH a la Trenicki. This one, where all the indices are different, if the R's are uncorrelated, this is 0. So that's the question about whether I was putting an R or not. This would be 0, and we don't find any reason why it should be 0. The twirling thing doesn't kill it. On the contrary, it leaves it invariant. How do I know? I do little blocks, I put them where I have to put them, take the average, okay? And very well. Now I go to this expression. Remember, I'm doing exactly now the same. I'm going here, expressing this in terms of sums with equal indices, different indices, all the possibilities. And then I am twirling the A's to see who survives. The first thing, because I don't have the time, that you very quickly convince yourself is that this one, although it has no reason to be 0, has less sums in it. So this one is okay, but it's subdominant. And then another thing which you realize by the same token is that I have 20 minutes, yes, 15. So this one we will not consider because it's subdominant. Then we have other averages which are like this. Let me see where. That are like this. I can write the sum, but let me show you how it goes. This is a sum that goes like this. So that this I2 and this I2 repeat, and this I3 and this I3 repeat. And this gives you this diagram. And when you, this is not zero, definitely not zero, but you find when you plug them in there that the way it is constrained is such that the average is zero. How do you know? Because you put the u's inside, you go to the average of products of u's, and you find that that term is subdominant. So, and why is it zero? Because, not zero, sorry. Why is it subdominant? Because it has a crossing in the indices. If you are a physicist, like non-planar diagrams, in the appendix of the famous paper, but if you're a mathematician, like in free probability. On the other hand, you could have something like this. So I'm going to erase this. So this is not very hard to show because it has been already shown for full matrices with a hard measure. So it doesn't, there's nothing so much new. But then you can have a thing that has, I'm not going to write it because it's a long thing and I don't have the time, but that's a diagram like this. So the A's are concatenated in this way. Okay, so how does it work? Let's say this site is I, so you have I, something. A, something, I. This is this circuit that goes and comes back to I. Then you have this, let's call it J, Aij, Aji. And this is the point where you see these two things match. Now, are you convinced by because you're summing, you could sum over the I, so because you have many terms that are equal, that this sum, this product can be cut here, and you can consider that this diagram gives you to leading order the same thing as with a pieces cut. Call this I prime and J, and call this with I. So you can cut the diagram, and the averages you want are these and these over the U's. All this comes from how you average unitaries, okay? At the end of the day, when everything is said and done, what you discover is that to leading order, the contribution for these guys that you have to put here are all the averages that are made of cactus diagrams. This is a cactus diagram. Any other combination, like for example, having this is non-zero because it is connected, but it gives you a smaller contribution to that function. This one is an example of a non-cactus diagram that is still non-zero, but to leading order, it doesn't contribute. And so the rule is write all the cactus diagrams, and this will decide who enters the sum. And now cut the leaves of the cactus. So cut them like this. But if you cut the leaves of that cactus, the only thing you need to know is a circuit. If you know how to calculate the averages of a circuit, you know everything. But a circuit, now we have to make an ansatz. And I am going to write the ansatz. How do I do an ansatz? Well, you already saw it before. I'm going to do something reasonable, then I'm going to plug it into that formula and see that the thing works properly. The average is, so I'm going to, and the ansatz is not very, very surprising, but I need to find it because I'm going to get it wrong. So for this average, which is a leaf of the cactus, my ansatz is this is the average over the whole circle. And this is, sorry, the average over the whole circle is f of q of the differences. I say that it's a smooth sum. It's a smooth function of the average. And here I need to put, it would be so for q equals 2 is exactly the usual ETH. So again, this is a smooth function of the average energy density, and it depends on omega 1, 2, omega 2, 3, omega 3, q minus 1, q. This is the ansatz I make, and how do I make it? I copy Cergy. I just think that this scaling will be okay. Why is this power here? Because every integral, when I calculate an expectation, will carry its own entropy. So I want that only one entropy remains, and this is what I need to put. And this will work properly. The fact that it depends on differences, I'm doing an analogy with Cergy. The fact that it's smooth, I am doing again. So this is very natural. And then because of this beautiful property that every cactus can be expressed in terms of one leaf, it works. And now last step is to get this and plug it into that formula. And I discover, perhaps not surprisingly, that this is the Fourier transform with respect to all the variables of TQ. So the Fourier transform of that formula over there gives me this multi thing, and this is it. And that ends up the thing. Yes. Yes. So again, the multi-point correlations are telling me that what this has to be. And that's it. So for the OTOC, you see the OTOC is one of these with 4 times, well, repeated, but 4 times. I need to know this guy, and this guy is a 4-point correlation of the elements. So this was what I got wrong when I tried to do the formula with a 2-point function, 2-point Cergy ETH, and plug it into the OTOC. By the way, Silvia Papalardi with Tomasz Prosen and Frisch actually calculated the autocobalt spin chain and separated the terms that come from usual ETH and from this extra one with 4. And indeed, everything that is long time is dominated by these, as we expected. So, okay. So now, yeah, now 1 minute more to say. Everything I said about cactus diagrams, etc., is two things: is planar diagrams the way it was done by people in physics, and it is also the theory of free probability. And a cactus diagram, if you draw it in a different way, is a non-crossing partition in their language. It's very clear why it's the same thing. And free probability, because now a lot of terms enter, free probability is the bookkeeping instrument for all this mess. So we fell against our will into the hands of this free probability, where all the sums and the things and the generating functions, etc., many of those have been derived. So this is where free probability has entered through the window. I think I'd stop here. Thank you.
Were discussing these diagrams. Some of them vanished exact variant, and then.
Sorry?
When you were discussing these diagrams, some of them vanished exactly after the averaging. Some of them were invariant, and then some of them you said that they were subdominant. Subdominant in what parameter?
Because when I take this one and I put it in the sum over there, the sum is over the elements of the matrix. So it's subdominant in something to do with how many elements of the matrix there are in your sum. So it is something. So this one, well, the one with 4 is to leading order, the product of two, one with two with two, you know, but it's not exactly that, and the difference is tiny. Not tiny, it's tiny with risk for the purposes of calculating that function. So its contribution to correlations is tiny. It's not, things here are measured in how do they contribute to correlations. You see, this one, where is it? This one is tiny also because it has this tiny factor. But because there are many sums, its contribution is finite. That one is also tiny, but there are less sums and the contribution is smaller.
So you have always assumed that there is like one operator A. Could I have had like A and B and C and so on?
You could. I don't believe that we were discussing this. I don't know if this has been written, but you see the plan if you want to put more. I don't think it has been written explicitly. I don't think, but you see what the plan would be. And of course, the F functions are going to have mixed things inside and so on. Yeah.
And the other question is, so, I mean, if we have a little bit more concept quantities than just energy, like let's say the number of particles or something, we could, in principle, have a chemical potential, right? And so how do I put chemical potential in all of this?
Yeah, we didn't explicitly do anything of the sort because we said, well, okay, for first trial, we fix the number of particles and work in the microcanonical, let's say. And with the number of particles, it's easy to do, not with energies. And okay, but with in the canonical version, it should be doable, but you have to repeat this reasoning and see what things you have to. What I would say is that this what you don't want is that there are matrix elements that connect in a strong way different classical energies, let's say different extensive energies. And I would say that the same is true of everything else. You don't, of course you can construct a matrix that does that, but that will never arise from a decent operator.
So even for the standard ETH, that like what is the status of like chemical potential in the standard ETH even?
That I don't know, but probably in the review you will find something said about this, I guess.
Thank you.
About integrable models, two things. One is that ETH doesn't hold. There is a work by Fabian Essler that is horrific, where really all the matrix elements, but it's a complete nightmare, and it's very complicated what comes out. On the other hand, it seems to be the case that if you get an integrable model and you perturb it with one spin, it becomes ETH. Something like that. But, okay.
Yeah.
So is cutting the cactus an exact property of Haar averaging, or are you throwing away some cumulant when you?
Yeah, higher order ones, higher order approximations, but the leading approximation for the purposes of calculating that, you can cut that, but it is an asymptotic property.
Thanks.
And in fact, the leaf of the cactus is the free cumulant. It's what is called a free cumulant.
Yeah. Jacopo.
Okay, so two things. So first of all, in order to connect with the topic of the conference, now, I mean, if you want to include like a U1 charge, then of course you would have to repeat this with like some U1 conserving unitaries, right? Yes. And this would be all the chapter of getting the hydrodynamic tails from ATH. And is it do I understand correctly?
Yes, yes, you could. It's again the thing of having conserved quantities. But at any rate, at the end of the day, where the physics appears is here, no? And this is what hydrodynamics has to give you. Physics is here, and we are just saying how it translates into properties of the matrix elements. So hydrodynamics could very well be here. But the question of conserving extra quantities, one first has to work out this program with conserved quantities. Yes, I don't see that there are going to be enormous objections, just you have to find how to do it.
And another comment maybe about the integrability. So, because it seems to me that the difference between what you do and Fabian, I mean, here the key point is that indeed you add the small perturbation and this gives you some coarse graining over which you do randomness.
But if the system is integrable, this can be cruel.
Yeah, but I mean, but of course, I mean, but it's clear that you have to coarse grain a bit to do this kind of, to get something meaningful. That's in integrable system, people don't do it. They just take the raw data. So there are actually perturbations that keep integrability at first order, for example, and this could be used to get universal stuff.
Yeah. Yeah. In integrability, what I imagine is that you would get some Swiss cheese structure with places that are precisely zero for mysterious reasons of integrability, matrix elements that are zero, and a big one on the side, or things like this, which in this kind of thing typically don't happen. But because things are protected by integrability, things can happen. But these things are easily destroyed also. So.
No, but all you have to do is just to choose perturbation that don't break integrability at the first order.
But, okay. Yeah.
And you can do it, it's known how to do it.
Fabian calculated exactly the elements, and this is a complete nightmare.
Okay, thank you, Jorge, for this. It was very nice. You touched a bit upon this free cumulance or free probability. It's very nice to see this connection. First question is whether does it provide you with some nice tools, then to compute things, like R transform, or I don't know. You mentioned some bookkeeping, but.
Yes, yes. The thing is that you need to do something for several operators, and the R transform is not easy to generalize if I am,
via rather combinatorial aspects, right?
Exactly. They work them as far as you can go, as far as you can go for the moment. So yes, we expect that things can be learned from what they have done. Of course, this talk with mathematicians, I would have them here completely sleeping, because this cannot be digested this way by mathematicians, sure.
Yeah, so that's a related question, also very vague, but the occurrence of free cumulants here, does it make some echo to the occurrence of free cumulants in the works on QSEP by Denis and others? Or
with the one of Denis, we haven't been able. We meaning them and us, we haven't been able to see the connection. We are convinced that there has to be one, and that what we are getting in energy has to be also possible to say in space. What I like is to think of when you have an observable, you don't have only that observable, you have a whole set of observables obtained by moving the electron around the room, and they are mutually free, which is sort of funny. And so maybe there is a way to put free probability in a nicer way in the whole thing.
Yeah. If you take this A as energy momentum tensor, and can you say anything interesting hydrodynamics from ETH?
I think that Mukund, I think that he's not here, no? He is there, yes. So the one time we talked, I remember that you said that for you too, it was good to use that kind of observables. Am I remembering correctly?
Well, if you want to use these things in the density operators split into pieces and thrown factorized between the operators, it gives you, as you said, regulated answers. It regulates UV divergences in the correlator.
I don't know where this comes from, on the other hand. Who did it? Who decided to
study this? Who decided to study this factorized form of the density?
Yeah, cutting the.
I thought, at least in the circles I know, it was this Malasena Stanford.
Sure, but
they motivated it precisely for this factorization.
Yeah.
For the UV regulating.
Yeah, but I thought that this came. I don't know.
I couldn't find in the literature someone who'd studied it before.
Okay. I don't know. I sometimes heard the name of Whiteman, but I never read that literature. So.
Well, Whiteman looked at general correlation functions.
Okay.
In Euclidean space, and he was interested in axioms for how these correlations could be used to reconstruct states, for example. And I don't think Whiteman ever thought about. He would not have written this. He would have written just a single row.
So it must have been Malasena and Schenker and Stanford, yes. But I think that this is, from the mathematical point of view, the most natural. And the way it simplifies calculations is remarkable. If you try to do the expansion when I plug in this into that, it's a festival of hyperbolic functions. And this way, it's nothing.
I mean, you could get rid of the hyperbolic functions by playing basis games even without splitting the density operator. This has been done by some people. So.
Maybe I have some confusion. So I distinctly remember a claim made in this conference itself that there is a version of ETH which is valid for GGE as well. And you seem to contradict that. So I just want
for GGE, no, for GGE, so from GGE, Marcos the other day gave me a paper of his where he gives, apparently I haven't yet read it, an argument that sort of kills it. But that tells you that is his only author. You probably know I don't know, where he convinces you that the diagonal elements in a subspace with all the constants fixed cannot be independent, but I don't know exactly the argument. So you can.
So all the steps that you did when you went from sum over eigenstates and integrals is what people do when do TBA.
Yeah.
And also, I mean, many years ago, I had a paper on spin chains. So you can compute the matrix elements. In the diagonal ones, you see that the variance shrink as you go to large system sizes. So
even keeping it integrable.
Yes, and actually even in Fabian's paper, and I also did for the spin chain, so we repeated what Fabian did for the spin chain. Actually, ETH holds to a degree that not even the diagonal elements become smooth as a function of energy, but also the off-diagonal ones, they decay exactly in the same way, so e to the minus s. The difference is that the statistics of what you had in what you call Rij, in ETH is assumed to be Gaussian. And in fact, for instance, Marcos has a paper where he shows that they are Gaussian. You can compute some ratios of cumulants and you see nicely. If you try to do the same for integrable systems, you see that distribution
is not Gaussian.
Is not Gaussian. So actually, Fabian finds for linear, he finds some Frechet distributions, and we for the spin chain, I mean, we are more consistent with some Gumbel distributions. So, but the basic, the backbone of the structure of ETH, it looks similar, very, very similar to also for integrable systems.
Okay.
Thank you. So if there are no further questions, let's thank Jorge again for a great talk.